아마 마이크가 들어오는 거 보니까 녹음이 되는 것 같아요. Let's get started. Welcome everyone. Make sure you are in the right video. This is not classical dynamics class. This is not classical class. This is QF class. So if you are in the wrong room, you have a chance to do that. T2. Okay, so that was really good.
메모리 다 여기 있는 것 같은데.
Quantitative theory too.
아까 메모리 같은 경우도 메모리인 줄 알고 이거
What's that?
봤는데 한
Are you supposed to be in the quantum field, relativistic quantum field theory class?
I'm
Okay, good. So then probably you want to go to the next room. I think there was a rule change recently. Okay, so then rest of you are supposed, I recognize most of you, except a few. So who were not sitting in my QFT1 class last semester? Probably you. Were you sitting in the QFT1 too?
I'm not.
You were not in the QFT1?
Yes.
But you're sort of familiar with some content of quantum field theory? Okay, good. So yes, this class is business fancy, but I want to be more classic. Yeah, this is QFT2 class. Hopefully you know me. Sure, most of you know me. Hopefully you know where I am in my office. Fifth floor. My office is. In case you want to drop by and ask any questions, and who I am this person, and I don't think you care, but I do theoretical particle physics. And office hour, well, after this class, as usual, you can grab me and ask questions. But if you have questions in the middle of not night, but during the day, then you really need to know the answer to, then you can email me or drop by and then see if you have a chance. Right, so this is a continuation of our journey that we took last semester. So in this class, we have to sort of finish up what we started off last semester, in a sense. So during the QFT1, we mostly dealt with QFT of a scalar field. So here we have to now develop the machinery to talk about the spinors and vector field. So we first want to go through the representation of Lorentz group, which we will talk about today. So what are the possible representations we can get out of Lorentz group? And two, once we do that, we will now delve into the discussion of fermions. So in particular, we are going to construct the theory of the Dirac fermion, we are going to construct the theory of Weyl fermion, okay? And then we will solve those, what is known as the Dirac equation and Weyl equation, then we will learn all sorts of properties of fermions. And after that, let's see, what do I want to do after that? I want to do that vectors, obviously. So here, obviously, there's notion of spin one particle, but crucially, we will now start talking about the notion of gauge invariance. Okay, and then once I have these machineries, I can put them together for the first time, to write down somewhat realistic theory called quantum electrodynamics. So at this stage, we're going to consider this classically. So we're going to look at the Lagrangian. We're going to look at the interactions among the particles involved in quantum electrodynamics. We can talk about the final rules. We can look at the processes like Coulomb scattering process and so on. So this is mostly classical. Then we will spend a lot of time talking about the concept of what's known as renormalization. This is a key concept that we want to conquer. So here, There's many concepts. There's loop diagrams. And then there's a shock under the name of divergences, meaning infinities. And there are many different kinds of divergences. There's UV, there's IR divergences, and then there's some other stuff too. There's what's known as collinear divergences. There's what's known as a soft divergence, and so on. But we are going to talk about those. We will mostly focus on UV and IR divergences. And then we have to know how to make a friend with the divergences. And that process of making a friend with the divergences is known as regularization. So if you fail to make a friend with the divergences, then you leave the field. Okay, there's no way you can survive without knowing how to make a friend with divergences. But once you make a friend with them, then you betray, you kick out your friend. That's the process of renormalization. So we will spend quite a bit of time understanding. There's many. So this part includes both a lot of technical steps. I mean, you have to learn how to compute things. Okay, you have to know mathematically how to control the divergences. You need to know how to mathematically get rid of divergences. So there's a technical part, but more crucially, there's a lot of a conceptual part. This is the part you can very easily get lost. Okay, you compute things, they don't know what you're talking about. Okay, so that conceptual part is key, and hopefully we will clear that up. And then once you finish this part, then maybe in the process of this, probably I have already talked about this, but then just do this way, and we will talk about pattern and role. In principle, entire quantum field theory can be start out with the pattern theory quantization, but we will lose a lot of conceptual understanding. So this will come together in a sense. And then I will go on to non-abelian gauge theory. So instead of a single photon field here, we will have a bunch of them, but combined in a consistent way. They're known as a non-abelian gauge theories. And standard model is based on that. The key example is SU2 gauge theory, SU3 gauge theory. In principle, one can talk about SU-UN gauge theory. But in principle, one can talk about some more general sorts of other groups. For instance, one can talk about SYN, SPN, E6, and so on and so forth. There's a lot of other groups in principle developed in our field, but I will focus on mostly SUN. Once I finish this, that's my big goal. Okay, so I shouldn't fail. At least going to that point, I'm famous not being able to cover what I promised, and I was pursuing my promise too. But by magic, if I ever get to that point, then we might have a chance. But don't dream. So why this is important? So at this point, you sort of know most of the ingredient that you can combine to construct, say, physics of the standard model and some of the beyond the standard model physics. But not quite. There are a couple of the concepts you need to know, and some of those important things, at least you know the keyword, are spontaneous symmetry breaking. As we know, our universe experienced that. There's a notion of anomaly, so there is a symmetry, but suffers from quantum mechanical violation. Relatively, there is a certain gauge configuration known as instantons, which are deeply related to the notion of anomaly. And there's a lot of more topics that can go on about the symmetry in principle. Okay, but again, this is your first and last time seeing these topics in this class. We will see, magic can happen, but not very frequently. So that's the tentative plan of the tentative plan of this lecture, this course. The basic material, which I picked up this book last semester, so I'm continuing to use this book, as you know, Coleman's QFT, but I will supplement it from some other sources. For instance, Pascal Schroeder and Stephen Weinberg's QFT books. I will combine some of topics from there. Okay, so that's how we start. Any questions? before we start? Good, let's get started. Okay, so now we're going to talk about the representation of Lorentz group. So you remember everything I said last semester. Too well that I don't have to repeat any stuff from there, right? You'll see. So here is the review. So what is the Lorentz group? Very quickly, this is a very quick summary. So I'm not going to derive any result. I'm just going to write down expressions that hopefully you find it familiar. Okay. So QFT is based on physics on the flat space and time. Okay, and then that flat space time has some name known as a Minkowski space and time. And there is a certain symmetry acting on this Minkowski, right? There is a certain symmetry transformation acting on this flat Minkowski space and time, and that is known as a Lorentz symmetry, or more generally, Poincare symmetry. So what is that? Given a lambda, and there is a 4 vector, which is element of the Minkowski space and time, you make a transformation. And then the set of such symmetries. Set of those such symmetries form a group known as a Lorentz group. Right? And the Lorentz group mathematically is SO 3,1. Okay? So what is SO 3,1? You take a x of mu, which is a 4 component. You rotate them among themselves. 3 components are space, 1 component temporal. So we distinguish space from the time just with this notation. You rotate them away in such a way that when you do it, you don't change metric. So there's the metric. And then you do make a transformation of this sort. And then under that, metric doesn't change. Okay, so that's the condition. And you collect all those transformations that satisfy this condition, and that is the Lorentz group, right? So we talked about that. And the defining expression for this, if I may write, goes like this. This is G mu nu, rho, mu sigma. This is nothing but this equation, if you do it. And then you take the determinant of this thing, you have to learn that determinant of lambda squared is 1. Okay, so now you can take a sector where determinant is equal to just +1 rather than -1, and that sector called proper. We'll combine it together. Now, by looking at the 0, 0 component of that equation, you'll learn that 0, 0 component of that transformation either greater than +1 or less than -1. So we take this sector, and that sector take, for instance, energy going back to positive energy. So we don't go back to the negative energy sector. And this one is called autochronos. So we look at the set of lambdas that satisfy both determinant equal to 1, which, by the way, means that it is a continuously connected to the identity. So that was the important feature, right? So transformation that is continuously connected to the identity operator, and that satisfies this condition. So that maybe we put plus sign somewhere. It's called the proper orthochronos Lorentz group. So today we're going to study representation. What are the possible states that is supported or allowed by this set of transformations? That is the goal of today's lecture. Now, the way we proceed from here is the following. By the way, just to mention, obviously, the whole group, by the way, the whole group is actually O 3,1. And then S is for spatial that satisfies this condition, right? So the entire Lorentz symmetry is this. And then once you understand the physics here, then you can go to other sectors of this O 3,1 by means of parity, time reversal, or combination of parity and time reversal, right? So there are 4 different patches. You can go from here to there.
Professor?
Yes.
Can you specify the notation of the metric? was that plus minus minus minus?
Oh, yes. So here I'm gonna use so this location. I think I'm using this. I'm gonna use this modulo minus sign, and I will make this less. Yes.
Why not representation of Bankai group?
No, no, good. So we can talk about that too, in fact. But we're gonna just focus on, so the only reason I focus on this is slightly saving some time and requires a little bit less technical discussion. But if you, all of you are like super eager to learn about the on-credit group, I can switch to. Okay, so the best representation, not in the sense of this representation, best presentation of on-credit group can be found in Weinberg chapter 2. But again, after this, if some of you are super duper interested in learning about that, which is very crucial, by the way, understanding, okay? Then, you know, I can sacrifice some of this list and then talk about that too. I mean, I'm happy. But there's no guarantee that I will be, you know, on plan. That's all. Any other question? So you talked about it, let me know. And then I cover it. All right, so I'm almost done with the review. So far, this is all review. So then what we said is that let's look at the infinite hexagonal transformation, which is close to identity, which is allowed to do so because I'm looking at the proper sector, right? Plus small. And then from the definition, one can learn that this parameter has to be antisymmetric, 4 by 4. What it means is that there are 6 parameters. Okay? There are 6 independent parameters, which is equal to 3 plus 3. Good. This is a correct equation. And as you will see, these 3 represents parameters associated with the rotations. And then these other, the separate 3 are associated with the boost, which will be the main object. Now, so far, this is about the Lorentz group, right? But we want to do the quantum field theory that realizes this symmetry. That means that for each lambda mu, we want to have a unitary operator that acts on the Hilbert space of the quantum field theory, right? So this is unitary because we want to do the quantum mechanics. Then this particular statement that lambda is 1 plus small value can be represented as some identity operator, again, acting on the Hilbert space. And then I just expanding to linear order in the omega. So I can put omega, but something has to balance that just by structure of the thing. And then this particular thing, again, this is operators, right? And this thing is known as generator. Once again, because of this antisymmetric property of omega, one can show that J also has to be antisymmetric, obviously, which means that we have a 6 independent and Hermitian generators. Okay, so there are 6, which is again equal to 3 plus 2, and Hermitian because unitary. So they are all Hermitian, unitarity of the U. There are 6 Hermitian generators, and then there are 3 rotation generators, and then there are 3 boost generators. So rotation generators can be written as, so given this, I take spatial component, and then I contract like that, and probably there's vectors overhead. Let me just make sure. And then I call J to maximally confuse you. Okay. So this is another 3 generator for rotation, and there are 3 boost. So boost, sorry. Let me take a Coleman's notation so that I can smoothly going over to the notation eventually. And then I have another 3 generators by taking, let me make sure, is it I0, 0I, because I don't want to mess up. Remember, there are 3 generators, which is the boost generators. So Lorentz group consists of these 6 generators. Okay, now. And then last semester we derived what sort of commutation relations these generators has to satisfy, L and M, okay, by studying how U should transform under Lorentz group itself, meaning by studying given a U lambda prime acted by, in the sandwiched way, another Lorentz transformation, which by group law must satisfy lambda prime, lambda inverse. Now you can expand this to be 1 plus omega prime. You can expand this to be 1 plus omega. You can look at the equations. Then you can derive Lorentz algebra. Which I will write it as a little so breaking down. Okay, so big So did I already? So this is a group notation. This will be algebra notation. Okay, so what is our? Hopefully you understand the group versus algebra. Group is like some manifold. Okay, and each of these points correspond to each of those group elements. Okay, so this is a space, if you like, manifold, differentiable manifold. Each of those entries correspond to the point here. And then one of the point is identity. And then you can certainly zoom in close to the identity. There's a tangent vector space. Okay, and there's vector space equipped with a certain, multiplication rules. So algebra has not only addition but also multiplication. So this vector space equipped with a certain multiplication property, so it's called algebra. But it is for this Lie group, or in this case Lorentz group, so it's called the Lie algebra or Lie. Yes, Lie algebra or Lorentz algebra. Okay. Anyway, so you can now, by studying this, you can derive Lorentz algebra, and let me just write down the answer. We have studied that. Okay, so then you can derive J I J K Y K I. Okay, so that's for the J, the rotation, and then O. Okay, I already messing up the notation, right? Very quickly. And absolutely nobody pointed out. Waiting to see if I'll continue with that or fix it. Thank you. Let me see. J. So don't consider. This is what I said about the multiplication rule here. This is like a product, right, of the element. So, okay. Anyway, so you realize that the first algebra is nothing but SU2 algebra, which we will talk about quite a bit today. And then the second thing you realize as given a vector, which is vector living here, and you take another transformation acting on it, and it goes back into a mixture of itself, right? So there's vector, rotate, goes back to itself. This basically tells you that this boost generator is a vector under SO3 rotation or SO3 rotation. That's what it means. This, if you do the booster together twice, then it can be represented by a single rotation. That's what it says. Okay, anyway, this is Lorentz algebra. Now we will study what are all possible, in a technical term, irreducible representations of this. Okay, so that's what we want to understand. Question. So far. Good. Now let's talk about the quantum field. So now we want to talk about QFT. So suppose we have a set of a field, which I combine into this notation phi sub A of X. Okay, so this is a multiplier field. I don't know, A component field. And somebody told me that this as a whole column vector transform in a nice way, in a proper way, under all of the Lorentz transformations. Okay, say somebody told you that. Now your job is to understand what that means and how to see that. All right. So what it means is the following. Remember, this is an operator in the Hilbert space, right? That you construct by taking a time flight, blah, blah. We have done all of that discussion last semester. What it means is that I take a U of lambda, so given Lorentz transformation, I act on it, like so. And then the effect of this transformation is shuffling component among themselves, right? For instance, if you had a vector, three vector, the three component, under the rotation, three component mixes up, right? Reshuffles. So exactly same way, Lorentz transformation will shuffle among these components. And then I can write as a mathematical expression as follows. So I just write, given lambda, there's some matrix that performs the shuffling among these components. So this is a statement that given a field transform under a given representation under Lorentz transformation, right? This is the statement. So this is a mathematical translation of the statement that I made here that somebody gave you of set of field, which is known to transform nicely under the Lorentz transformation. This is the statement. Is that clear so far? But I'm saying, hopefully this part is clear. This is like shuffling, right? If you're confused by this factor, I'm not going to tell you because I told you. So go back and check and ask if you still did that. Okay? Yes.
So do you need to define the representation of the field under the Lorentz field?
I'm basically along that direction to define what it means to be representation. But loosely speaking, at this stage of discussion that I'm trying to say, this is, in a sense, you can take it as a defining expression that phi furnishes a representation under a Lorentz transformation. Okay, because it does not go out of somewhere, right? So it transforms over themselves. It performs nicely. Yes.
The notation in the right-hand side is usually used for the linear transformation. So the linearity is assumption or it is a general principle?
Very good. So here I assume linear transformation. Yes, that's good. Yeah, so the question is, in principle, if you do that, some crazy shit can happen here, right? Some function of a phi, blah, blah. But I assume there's a nice linear representation. Any question?
Oh,
Yeah.
I'm a little bit confused. Isn't it lambda x, not lambda inverse x?
So that's the part. Yes, it is a lambda inverse x, and think about it.
But last semester it was lambda x.
No, last semester I also wrote lambda inverse x. So in particular, if you look at the part that I discussed, which is commas, okay. So suppose I have eventually I explain. Very good. That was a nice trick. So suppose I have a function. Okay. Then I want to perform a shift in this function by a constant vector a. So that means I want to get this. So I literally perform the shift by x. Sorry, a. So suppose this is a. Right? So now I'm asking you, in a functional form, what do I have to put here? And what I have to put here is I have to put f over x minus a. Did I say correct? F over x minus, yes, I did say correctly. So that this function, when the minima is a, right? This is, so that means that if I did a Lorentz transformation rotation by this, the functional form should be the opposite of the transformation. Right? I made a positive a translation, but this is appearing as if that I made a negative translation. Okay? So you can show me what I did last semester. Any other question? Okay, good. So what I am interested in, what we are interested in, is that I want to, I want to be able to construct a quantum field theory, right, as I want. Then you need to understand what are the all possible allowed building blocks, and then what are the all possible ways to combine them together. When I say building block, what are the all possible fields you can ever allow to use? So one of the things that we already talked about is a scalar, right? Okay, good. I know I'm allowed to use a scalar. You can ask yourself, what else can I use, right? And that is the question. So what are the all possible building blocks, in particular minimum building blocks, that I'm allowed to use to construct quantum field? So for instance, we talked about the scalar again, right? And one thing that you can imagine is that, yes, I heard of this vector density field. So yes, vector is allowed. And maybe we are allowed to talk about some tensor field. So these are the fields, sorry, in case most of them. So the question is, what's the least, right? In particular here, spinor field is missing, or the electron field, for instance. Some fermion field is missing. So how do I see that person fit into this picture? And that question, meaning understanding the entire set of irreducible representation or building block, this is a one-to-one map to understand all possible structure of this. Given a field, this controls how it transforms, right, under the Lorentz transformation. So understanding entire set of this minimal building block set, the same as understanding entire possible this representation matrix, D of lambda. Is that clear? Good.
Well, in that case, is the professor said that we assume that nice linear representation.
Yes.
Is that enough to those linear representations just cover all the transformation of the square vector tensor?
Good. In principle, it's not enough. In principle, and but most of the case, it is sufficient. Now, then the key concept into that part of the discussion is notion of a spontaneous symmetry breaking I wrote here. And when a symmetry is realized linearly, meaning it actually as a linear transformation, then this is what we're talking about. Sometimes the symmetry can be realized non-linearly. Now there can be product of field appearing together to transform under the group symmetry transformation. Those are called non-linear realization of the symmetry. And that happens, for instance, a given symmetry is spontaneously broken. Okay, so a lot of times this is sufficient, especially for space-time symmetry. In really most of the cases that you will see, this might be enough. Although this is not absolutely the entire set of consideration. People have thought about that there's a space-time symmetry which is bigger than Poincare group that we're talking about, which is spontaneously broken down to the Poincare group. So there's a spontaneous symmetry breaking, there's a non-linear realization. So people certainly thought about that. But that's really like in the corner of the quantum field theory. And who knows, it may be what's described in this universe. There's no guarantee. But let's first understand linear first. And then you have a chance to understand spontaneous symmetry breaking as a bullet point 8. Then you can come back to this question and think about on your way whether slightly more general consideration can be done. Well, this is not the entire set, but this is a big enough set that will cover us a lot of aspects. Okay. So then in the rest of this today's lecture and perhaps next, we will basically try to understand what are all possible this representation metrics. Yes.
Can I say that the matrix D is a representation of the transform U lambda?
Yes. So yes, it is. So there's a two-step map. There's a lambda, and then we construct the U of lambda as an operator realization of that thing that acts on the Hilbert space. Then, given a specific field, then I need to know how it actually acts on it. So D is a representation of this U. Okay, so in fact, since that was said, exactly so. So given say 3, for instance, there was okay, so this is derived from the fact that there was this multiplication rule of the group that D don't satisfy. So we demand that it to satisfy its property in order to be a representation. And also, if I take identity operator, it should be realized as an identity operator on the Hilbert space. Then D of 1 or lambda equals 1 obviously must be realized as, let me write it as a 105 in the sense that this is identity matrix that acts on not the Hilbert space, but in the field space. Right? So here in this space, the coordinate is the multiplet of the field. And then that identity operator is what's rotating in that space. So it's a field space identity. So indeed, D is, if you like, so since we're talking about representation, let me note a couple of notions. So a couple of definitions. So first, a representation of a group. What does that mean? In case you haven't thought about it, a representation of a group G, for instance, means that for each group element G, which is element of group G, then there exists, if you like, which is a matrix. To be honest, the mathematical notion, I don't know who of you are like mathematically including the person, mathematically representation need not be a matrix representation, but we will be only thinking about matrix representation. If you're a math person, you are looking for a group homeomorphism, what are you talking about? No, so I'm a physicist. I'm happy to speak that language too, but let me pretend I'm a damn physicist. So I'm talking about just a set of matrices for each of the G, okay, that acts on the vector space. So I'm thinking about matrix representation. Obviously, since I'm talking about the group, that means that given a G1, G2, and G3, that satisfies G1, G2 times G3, G1 times G2 is G3, group multiplication, then representation has to fulfill the multiplication rule. And then obviously there is, there is identity, there is an inverse, there is associativity, the axioms of a group. It has to all fulfill here. Okay? So basically, therefore, what I'm saying is that a representation means that for any element of the group, in this case, Lorentz transformation, we will have a matrix that acts on the field space in such a way that it satisfies group multiplication, identity, which I wrote here, and then inverse, and then associativity, as the groups has to satisfy. Okay? That's what I'm thinking. There are a couple more, otherwise I wouldn't have put one there. So let me list a couple of notions so we can speak the same language.
Can I ask one thing?
Yes, you can ask two things too.
So, why do you believe that? Why do you believe that the Lorentz transformation doesn't change the value of the field?
It does change. Sorry.
So, if we assume that d of lambda is 1, identity for all lambda,
Yeah.
then we will assume that the phi field will not change in the Lorentz transform.
Mhm.
But I think if the observer doesn't change under the Lorentz transform, then it is okay.
Good. First of all, under the Lorentz transformation, are you trying to say that so long as I can construct the formalism where field changes under the Lorentz transformation, but it leaves the observable invariant, wouldn't that be a good formalism? Is that what you're thinking?
Yes, that's right.
Good. So there is that notion actually. There is that notion. Okay, let me finish. So in fact, yes, we are using quantum field as a building block of quantum and relativistic physics with observables. What we care is that the observables satisfy the sacred principles. And then the first 2 weeks or 3 weeks of the last semester lecture was that what economic way of assuring this property that observable all satisfy the principles that we want to satisfy is in terms of quantum field that satisfies the property that I'm describing now. So it guarantees that give you what I want in terms of a quantum observable. Now, if your question is mathematically the unique solution to get there or something else, that I don't know. That you may want to think about, maybe meaningful thing to think about. But as far as I can tell, if I want to describe a set of particles, which is a relativistic quantum mechanical, the construction that we went through last semester, we're continuing this semester, is almost unique answer to that question. Because if there's a particle which is created explicitly and directly from the quantum field, and I know how particles should behave under the Lorentz transformation, that means that explicitly I know how quantum field which excites the particle has to transform under a certain format. So in that sense, there's a stronger link because we are not just talking about a random observable. We are talking about explicitly particle state that are created by this quantum field. So in that sense, there's a sharpening process that lead us to think about explicitly this way. Thank you. Yeah. Any other questions? Okay, so one thing that I must say, by the way, this is in PES. So when I say, given this must be the case, this is not the most general possibility. Remember, okay, probably I should move on. Let me just say that in quantum mechanics, states are defined as array, not as a vector. Right? So given a state vector, I can multiply by random U1 phase, it doesn't change anything. That means that if I have a quantum state, and then I transform by this, and then the fact that I go back to the equivalent state means that this times arbitrary phases allowed. Right? So if I multiply my quantum state, so this is equivalent to that phase. Right? And in fact, this phase can be a function of this too. And there are group and representation where this phase appears, and those of representation is called projective representation. And there's a certain mathematical discussion when you do that. In some group and some representation, you can always get rid of those phases by properly defining generators of the group. In that case, it is just not projective representation. So whenever you can get rid of all those phases, those are not projective representations. But in certain cases, no matter what you do, topological obstruction is there so that you can never get rid of those phases, that it is intrinsically projective representation. And Lorentz group that we are discussing is actually intrinsically projective representation. Okay, I just said a lot of words. Okay, forget all that. If you're curious, you can look at the section 2.7 of Weinberg. He has a nice discussion. Okay. Yes, guys. Okay, so second definition regarding representation, there is notion of a faithful and unfaithful representation. So this means that suppose I get two representations, and I found that they're associated with two different group elements. I found that the representations are the same. And faithful, the representation is faithful only if this is the case. Okay. On the other hand, obviously, if for the same representation, even when lambda is not equal to lambda prime, such a representation is called unfaithful representation. For instance, suppose I take a set of elements of the group, and then I just I just assign that to be the identity operator, or in this case D, because I'm using D. For all lambda, then this is maximally unfaithful, right? Because I have a million different lambdas, they all go to the same element in representation.
Can I understand that the base pair as a statement that D is injected?
Yes, it is injective is probably the right word. Although, yes, I think it's injective. Okay. Notion number 3, there is notion of equivalent representation. So, given, suppose I have a 2 representation of 2 elements. If there exists invertible matrix T such that you can get this relation when given 2 object. Sorry, I should have said slightly. Okay, hold on a second. Prime should be here. That changes a lot of meaning. Let me say that again. I take the 2 in the same element, okay? And then this applies for every element of the group that I'm interested in. And then I'm looking at the representation, which apparently, or at least, whose appearance looks different. Suppose you look at the matrix structure, entries here are different from this matrix, for instance. Okay? However, what I'm trying to say is that if there exists an invertible matrix in such a way that it relates these 2 different, naively different looking representations, then we say that D is equivalent to D prime. And then we write from now on as this notation. Okay, so probably you have heard of notion that this is similarity transformation, right? So in that sense, it's the same. And another way of you can think about this is that this is going to act on the field space, right? So D acts on in the simplified notation like that, right? Then basically using D versus D prime is the same as so basically you're making change of bases in the field space. In that sense, it is equivalent. Okay, yet another notion, definition. So there's this notion of a direct sum and then associated reducibility or irreducibility. So what do I mean by that? So suppose I am given a D of lambda, and then suppose this is equivalent to slightly different representation. Oops. It doesn't matter. Suppose I just take that and then I did some proper similarity transformation in such a way that instead in that basis, turns out that this thing can be written as this black diagonal. Okay. So the only reason I went through this first step is just to show that the notion is always up to equivalence. That's what I mean, right? But given a D, the question is, can I find a basis through this similarity transformation in which that representation is decomposed into a block diagonal form? Then we say that this is a direct sum of D1 and D2. And in mathematical notation, we write it as this is the direct sum of the 2. Operationally, what it means is the following. So suppose I take this thing and it acts on the field space. So let me even decompose that also as a phi1 and phi2, right? So I started out with some big phi, and then I decompose it as phi1, phi2. And you see that this guy only acts here, and then it shuffles only among themselves. And this guy only acts here, or shuffle among themselves, right? So this will never mix with that. So there is a factorization or decomposition of the vector space into phi1 and phi2. And in mathematical terms, we say that this is invariant vector space. Under the symmetric transformation, they only just shuffling among themselves. So when we talk about, therefore, or when we are interested in figuring out what is the minimal building block, we don't have to carry around all this black diagonal, right? Because it manifests into two separate, smaller, minimal building blocks. So when this happens, we say that this B is a reducible, in the sense that reducible into D1 or D2 separately. And in a similar token, when D can never be written any choice of similarity transformation into a black diagonal form, then obviously we say that that representation is irreducible representation. Because I cannot reduce further to a smaller invariant vector space. Is that clear? Good. So let me say one thing. By the way, in the physics literature, never probably in the math literature, when you first try to learn the group theory, this word, the representation, is the maximally confusing word because people use it very different way, right? And if you first learn the group theory from the math paper, it's always like given a group element, there's a group homomorphism to that and that. But if you open the physics book, they never talk about this particular version of the representation. And this is the definition. What the hell is going on? So here I use the representation in a mathematics friendly sense. I'm actually talking about that thing. But in physics, we also talk about figuring out this is also representation. So either understanding actual alteration of the symmetry or the vector space that it acted by, both are called just representation in physics. Okay, just keep that in mind. Okay. All right. So with that, so far we prepared. We good to go now. So therefore, now I can say a word. The original question that I wanted to address was that given this Lorentz group, we wanted to understand what are all possible minimal building blocks of the QFT. And then I say that that question is equivalent to figuring out all possible minimal building blocks of D of lambda. And then I don't want to carry around equivalent representations because I just need to keep only one. Why would I carry about infinitely many equivalent representations? Also, I don't want to carry around all these reducible or direct sum representations. So therefore, the question is, what are the all possible equivalent, irreducible representations of the Lorentz group? Because that's the task we want to tackle.
Professor?
Yes.
It's very complex that you're considering a set of fields, P,
Yes.
A,
Yes.
and so what is the meaning of index A? It is kind of what's that? Particle, is it a particle or spin or what?
Very good. So eventually, in the context of Lorentz transformation we're talking about, it will be associated with the spin degree of freedom. Okay. I said, okay, so it's a slightly subtle learn than what I just said. So it is a component of the field that gets shuffled or mixed up by either rotation or boost. Right? That's exactly how I define, right? Phi over A that gets reshuffled by U over lambda. Now, sometimes that component will be called as a spin degree of freedom. And this is the case when I'm talking about massive particle states. And then I will talk about helicity degree of freedom, this component, there's a different name, when I'm talking about massless degree of freedom. But other than that, it's all related to, say, spin in quant, roughly speaking. Any other question?
So, 선생님, 결국엔 레프레젠테이션을 스페이스로 쓴다고 했는데,
Sorry, say it again.
레프레젠테이션을 이제 비밀 말고도 스테이트에서도 쓴다고 하신 거예요. 그러니까, 블록 다이고널이 되는 T가 존재했을 때 그걸 베이시스 같은 거를 레프레젠테이션이라고 얘기하는 거예요.
That's exactly correct what I said. Yes. In other words, if you can either construct this matrix form, or you can construct the basis. But if you have a basis, you can always read off the matrix entries by sandwiching. Right? There's an operator, there's a sandwich by the two basis vectors. That is exactly ij component of the matrix. So it captures the equivalent information. That's why in physics, we are loose sort of people. When it comes to this sort of discussion, we just call both to be representation. Although in technical terms, we call representation space, and then whatever representation, but we just usually call representation. All right. Okay, so much about the nomenclature. So let's actually not talk about representation of both bars. So by which I mean, hopefully you understand irreducible representations. Let's talk about irreducible representations of lowest group, and then I put SO3, with quad. We'll see why. Quad. Usually you see quad when it's almost correct, but there's a slightly some subtlety in it, right? Yes.
SO3, 1 or SO3, 1 plus.
Oh, sure. So that's not the reason why I put the quad, but yes, it's good. Another question. All right. So let's recall the algebra. Well, I erased really the figures on both sides. I can write it again. This was the Lorentz algebra. Yeah. So basically, the way I will work out, first of all, sort of trying to understand this side of the story. Okay. Well, not quite, but okay, I will conquer both of them in a sense simultaneously. So now, this is complicated looking algebra. Even though it's not the worst kind of algebra that we can encounter. One nice way of arranging this thing is as follows. So, like I said, this is, if you like, this algebra. Now, let me define J plus n minus vector. By vector, I mean there's ijk as L plus minus M. Okay, I combined it. In terms of, I mean, the inverse relation is simple to write also, so let me write, because both are important to see and use it. Okay. So literally, I take the inverse relation. So nice thing about this redefinition is that, remember, what I just did was literally, I took a vector space, which is called algebra, right? And then I defined a new basis in the vector space, although I did something funny about this because I did not make a real linear combinations of it, but I make complex linear combinations of it. So in a sense, I complexified the group. Forget what I just said. I did something. So if you do that, then you can check that now the algebra satisfies the following relation. Okay, so this algebra becomes that. Okay, so what have I achieved? Well, this is SU2, but let me put plus because it's for plus J plus. This is also SU2 among the minuses. And the last statement says that the first SU2 has nothing to do with the second SU2. They exactly commute, right? So that means that this last point shows overall that SO31, which I will show, is equivalent to SU2 times SU2. Okay, actually, one has to be careful. What I really wanted to say is that the reason why I say be careful is I think in the algebra sense it should be direct sum, but it becomes a direct product if you go to the group space. But okay, you understand what I'm saying. There are the two separate SU2 vectors. That's all I'm saying. Why this is great? This looked like a very complicated question to tackle, right? Well, oh, irreducible Lorentz group. But you understand everything about SU2. So once you know how to do it twice, totally independent way, then you can get every representation of the Lorentz group. Right? That's the beauty of this construction. So let's do it. So do we have a okay? I'm just gonna do until you say no. I mean, when am I supposed to stop? Just 45. Okay, good. That means I have 20 minutes left. Okay, okay, let's do it. So let's talk about the irreducible SU2 briefly. Only super briefly. You all know, right? So given a single SU2 algebra, what do? You learn this. First of all, you construct the J plus minus, which is 1 over square root of 2, and J1 plus minus IJ2. Then you check that this satisfies a nice creation and annihilation algebra, as you have seen. And then there's one special operator called the J square, which is obviously, some square. Then you organize your representation as there's a J, there's M, right? And then if you take J squared, obviously you get this. After all this writing, I'll say something. In a language that I'm not sure if you have heard of before, I'll say something. And then you learn that J plus minus basically raises or lowers this M. And then you can check that, demanding that there's a unitary finite dimension representation, you can check that spin J representation has a dimension 2J. So these are the list of probably you have seen or have derived for quantum mechanics class. Okay. Now, I'll just say a couple of words in a language that hopefully useful. No, so let me explain. Well, right. There are two keywords, but I'm not gonna do that. So then this is irreps of SU2. Now there's a subtlety about SU2 versus SO3, which also you have seen it, right? So you have seen this mysterious or a fancy word saying that SU2 is a double cover of SO3, right? You have seen that in quantum mechanics class. Mathematically, that is written as this expression, which also hopefully you have seen that before. Now, let me already say something at this level, and then I will actually derive this fact, okay, which will be carried over into the Lorentz group structure too immediately, which is crucial. Now, SO3, what is this? This is a group that rotates three-dimensional vectors together, right? In other words, let me say it again. The minimal dimensional representation of SO3 is a 3 by 3. Right? This is the definition. This is a three-dimensional orthogonal group. And then you can have a higher dimensional representation constructed out of this three-dimensional vector representation. So here, minimum representation is a vector representation, which is 3D. Okay? Here, this is a matrix of a 2 by 2, but complex. So you can here talk about the two-dimensional representation. Because you can have a vector that is rotated by 2 by 2 complex rotation. So here the minimum representation is a 2D rotation, 2D representation. In this case, this is a 2D spinor representation. So what's the difference between the two? So vector representation in that language has a spin equal to 1. And it has a 3 component. That's how I figured out J is equal to 1, right? 2J plus 1 equal to 3. So J is 1. So it's a spin 1 representation. Yes? So if you leave it on this side, then you can construct higher dimensional object as a tensor product of the vectors, like, V mu, you can construct a 2 tensor object out of it. For instance, keep going. So therefore, in this chain of thought, in other words, if you lock yourself in SO3 world, what you can get is you can get J equal to 1, 2, well, we can have 0, 2. So you can only get integer spin representations. Is that clear? Yeah. So there's a minimal representation. You construct the rest by tensor product. Okay. So here only you can get integer spin states. Here you start out with a two-dimensional minimal representation whose fast name is a spin representation, and then 2. So if you plug in 2, so 2J plus equal to 2. Can I solve this? Yes. So then that tells me half. Okay? There's a half spin state leaving SU2. And then you can also do tensor producting it together. Spin representations, you can construct the rest of the representations. So here you can get 0, 1/2, 1, 3/2, etc. So in particular, if you're living here, you are missing spinor representations or half integer spin representations. Okay, so this modified 2 basically projects out all these half integer spin things. Now I'm about to show why that's the case. But I'm just saying already, just from the fact that there's a dimension, there's that formula, I can already talk about that. Okay? Now, the way that will play eventually to anticipate our discussion is that if you look at the SO3,1, so let me just write here. Is blue good color? I like green. Anyway. So SO3,1. So if you live in SO3,1 world, meaning you just insist, give me all possible state allowed by SO3,1. Then again, you will get only integer spin particles. Just like SO3. Okay? And then I will show you that this is equivalent to, instead of SU2, SL2, C plus Z2. What is the special determinant equal to 1? Linear matrix multiplication, 2 by 2 complex matrix. So here you can get all half integer space. And then the relation between the two is okay. I will show a modified 2, but also when you take SO3,1 algebra, if you complexify it, whatever that means, you can get that. And secretly, I have done that to you. I told you. I said that word once. So that's why all of a sudden, oh, wow, why did I get SU2, SU2? It looks like you can get all spins, right? SU2, SU2. But secretly, that's what happened. And then my job is to demonstrate how that happened and why they can be possible. Okay. So question.
So the SL2C is the weak groups generated by the SO2, IC2 time SC2 plus SC2.
So the Lorentz group is generated by SC2 and is what you're saying?
Yes, so this SL2C is generated by the SC2 times.
That's correct. That's correct. Yes. So good. So the difference between group structure, which has non-trivial this thing, right? So it's called the global structure of the group, versus algebra is that algebra is a local information, as I told you. You just look at the point very close to the identity. So it doesn't know, globally what happens, what is non-trivial connections and topologies and stuff. It doesn't know. So given a same algebra, which can generate either SL3,1 Lorentz, or it can also generate SL2C. The difference between the two, starting out with the same algebra, is what sort of a topological difference can be there. Okay, so that's so in that sense, we say that SL2C is a double cover of a Lorentz group. Only then you have a spinor representations. Okay, so let's see. Okay, so I have 5 minutes. 15? Okay, unless I'm kicked out. All right, so let me demonstrate this. Okay, and then I will take up from this point next time and then finish up the representation. Okay? Okay, so let's look at that double cover structure. So take for any given vector, okay, which for SL3. So I'm taking a three component vector. Okay, that gets rotated by SL3 rotations. What I can do is that for any given V, I can always construct little v by contracting with the Pauli matrices. So in explicit components, this looks like B3, B1 minus B2. So what I'm saying is following. Given a 3-dimensional column vector, there's a map, 1-to-1 map from that and little v, which is now 2 by 2. There are 2 important factors. First, it's a traceless, because all Pauli matrices are traceless, and then Hermitian. Okay. So now, since this is not 2 by 2, which is 1-to-1 to the 3-dimensional vector, what I can imagine is that given V, I can now transform some 2 by 2 complex matrix for now. This is arbitrary for now. 2 by 2 complex matrix, B lambda dagger. Obviously, if I do that, it will shuffle around all these entries, right? If I take 2 by 2 complex matrix and then do this adjoint transformation, it will shuffle all these entries. So from that point of view, looks like what it has done is, so this I can rewrite as Vi sigma I this. Once again, it looks like it's shuffling around all the entries. It looks like what's happening here is that there's some matrix that shuffles around the V. And then I can always rewrite what happened here in this form, right? I can always just rewrite this. So there's some chance, therefore, which I will discover is the case, that certain kind of lambdas, which I will determine what certain kind of lambdas, can actually incorporate SL3 rotations. So let's see what certain kind of lambda can actually achieve this. That certain kind of lambda has to satisfy A 2 by 2, which is the case. It should be traceless. It should leave, let's actually do. So it should leave traceless vector into, sorry, traceless 2 by 2 V into traceless V or so, but that goes like this. Then by cyclicity of the trace, I can write it as the dagger lambda V. And I want to demand that they don't change the trace. What it means is that lambda has to satisfy this condition. That means lambda A is a unitary matrix. Okay? So demanding the first condition says that lambda should be element of a unitary matrix. B. In SO3 sense, remember, I don't want to change the norm of the vector, right? That's the orthogonal transformation. Okay, so I don't want to change this, but that means one has to remember, one has to realize is that this is equal to this norm. You can check determinant of this little b. I mean, you already can see that. D3 squared minus b1 plus b1 squared plus b2 squared. Okay, that is therefore normal vector. So the fact that non-preserving transformation, which is defining property of SO3, right? This is orthogonal transformation, means that determinant should not change. Correct? So I want to have determinant of preserving transformation. So that means this. And so that means determinant of lambda has to be this. Because this is product of the square of the determinant of lambda and determinant of b. Okay? I'm almost there. However, you note the following. Since b transforms like this, so lambda and any U1 space times lambda performs the same transformation. Right, because phase cancels. So I can make use of a phase freedom to already choose, so use this freedom. To choose determinant lambda to be just 1. Okay, I can already arrange that. So at this point, we conclude that lambda being element of SU2, therefore looks like incorporating actually SO3 transformation here. Okay? But now there's a caveat. Even after I use of this phase freedom, still there's something left over, which is to say that lambda and minus lambda, even after this, lambda and minus lambda associated with the same rotation. Remember, I'm talking about 2 by. You might say, oh, is this determined to 1? I'm leaving the two-dimensional, right? So -1 minus 1 determinant is +1. So even after making this, lambda and minus lambda in SU2 sense corresponds to the same SO3 rotations. So there's always 2 elements in SU2 side that give rise to a single guy in the SO3 side. So that's the sense. Start hearing sound. Suggest that first of all, I wrote this. Okay, and finally, let me just demonstrate one quickly. So one specific element, which I take to be rotation around the z-axis, which is generated by this, right? So there's a 2 by 2 Hermitian matrix, sorry, 2 by 2 unitary matrix generated by the z direction rotation with angle theta. And then you can write this as either I theta over 2, either the minus I theta over 2, right? Because this is a +1 -1 along the diagonal. Now let's make a 2-pi rotation. Right? A in SO3 sense, meaning you're literally making a rotation in 3-dimensional space sense. Obviously, if you go around the 2-pi, you have to go back yourself, right? So you expect that this should be equal to 1. So this is expect. But obviously, in SU2 sense, if you literally compute this, lambda with the theta equal to 2-pi, what you get is a -1. Okay? So starting from the origin, if you make a 2-pi rotation, in SU2 rotation, you're just going back to the halfway, going to the -1, and then you have to make 4 pi to go back to your cell. So it's a two folding. Okay, but also this also shows that in SU2 rotation, there's a certain state that under the 2 pi rotation, you pick up the minus sign phase. And all those representations, as you will see, are the spin representations, spin half representations. Okay, so I will finish here, and next time I will pick up this discussion for Lorentz, and I will finish representations. That's all for today.